Okay, so let's get started. We're going to be taking a look at working with our Lambda Target Overlay Table feature found within our Link, G5, and G4X programming. Now, our Lambda Target Overlay Table can be applied whether we're in modeled or traditional fuel equation modes. We'll find that typically when we're in a modeled mode, I do implement this table because it makes a lot more sense. It's part of our fueling calculations, so this is going to be something I'm going to turn on in here in a second. Now, before I do that, I just want to quickly go over our air and fuel model that we have within our model mode, just so this is going to make a little bit more sense as to how this table actually works and why we want to implement it. So we've talked about this pretty extensively, but we have an underlying equation here. Fuel mass is equal to air mass divided by target air fuel. The air mass is going to be coming from our fuel main parameters here, also in conjunction with our volumetric efficiency percentages from our table. So that's going to give us the estimated air mass. Now we specify the desired target air fuel based on knowing our lambda target and multiplying that by our fuel stowage. So if we know air mass, we know target air fuel, we can calculate a fuel mass. Now we turn the fuel mass into an injector pulse width here in the modeled mode based on knowing the injector flow, as well as knowing our fuel characteristics here, so the density and temperature coefficient. And then we also have to add the injector dead time and short pulse width to the base pulse width we calculate. And that gives us our injection actual pulse width. So we can see here, I have the engine simulator running right now with my G5. The injection effective pulse width is calculated as 0.58 milliseconds. The dead time is calculated at approximately 1.288 milliseconds. So the actual pulse width it's sending to the injector here is 1.87 milliseconds. So we can see kind of how that flow of logic is going to work. Now, when we have our desired target lambda table here, if we jump into fuel, we have our lambda target air fuel table. We can see here at idle, we're commanding 1.0 lambda. If we're running our engine in a situation where it's cold, we don't necessarily want to target 1.0 lambda. We want to richen up our mixture a little bit. This gives us an improvement in our engine stability, as well as giving a little bit more engine torque output out of the engine. When we fire up an engine, there's going to be frictional losses for a cold engine. Engine hasn't warmed up yet, so the engine's going to want to idle a little bit lower. We can offset some of that lost torque output from frictional losses on a cold engine by running a little bit richer target lambda target air fuel mixture. Now, if you recall, once we've calibrated our main volumetric efficiency table here, so that's going to mean we pay attention to what the actual lambda is showing us, we compare it to the target, and we adjust our VE table values here, depending on the particular cell point location in the table. You'll adjust your values so that your actual and target are matching each other. That means that your table is dialed in 100%. If we want to change our desired target lambda at any operation range within our table here, we can do so after changing and dialing in our VE table here. We can dial in a new target air fuel without having to retouch or readjust our main VE table, because this represents estimated air mass. This represents target air fuel. So they're separate in that equation of fuel mass is equal to air mass divided by target air fuel. Now, the significance of this is that when we're talking about a target lambda overlay table, we're able to provide a condition that we can offset our desired target air fuel here, target lambda, when the engine is running, let's say, in a cold warmed up condition. So we want to implement the overlay table. There's various different things we can do with it, but generally we implement the overlay table when we want to offset our desired target lambda when the engine is cold and it's warming up. Let's explore this and see how this is going to go. So I'm going to jump over here to basics. Let's jump down here into fuel main, and let's go over here to our lambda target overlay, and let's turn this on. So it's right now off. We're going to set it to always on, and then click yes. Now when we do this, if we jump here into closed loop fuel, this is going to show us our open loop target lambda table. So let me go ahead and expand this table out just a little bit so we can take a look at this. Now this table, the way it defaults, is going to be based on, in this case, engine speed at the top, and then engine coolant temperature here on the side axes. Now that's the intended purpose for this table. So they're going to be saying, we're able to use this to offset the desired target lambda in cold running conditions for our engine, And then when the engine's warmed up and it's running, it's not cold, then we can just ride purely off of our airfield targets here. Recall that when we were just discussing this, we've dialed in our main fuel table, our main V table. We know we have our desired target air fuel lambda specified here. If we want to change the desired target lambda air fuel, we do not have to go in and retune our V table. All we have to do is change it, let's say from 1.0 lambda stoichiometric to 0.9, and that'll automatically adjust our fueling calculation. We can actually see that right here. So let's assume at idle here, I've dialed my values in here to roughly 63, 66%. Previously it was at 1.0 lambda. And we're taking a look at our actual pulse width here. So it's 1.87. If I command a lower number here, that's going to command a richer target lambda mixture, what we'll find is that this pulse width will increase. It'll do that specific to the exact amount of pulse width that has to happen, the exact amount of fuel flow that has to happen in this math modeled system in order to hit this desired target lambda. So let's try this real quick. I'm going to go here from 1.0 to 0.9 lambda. And if I click enter, notice that the pulse width goes up here to 1.96. So
thanks for checking out our teaser clip. If you want to see the rest of this video and more than 500 hours of current EFI training we have to offer, make sure you click right here. If you want to go and check out more teaser clips from this training course, click here. And you don't want to miss any of the videos we're going to be releasing on this channel, so make sure you subscribe and click here. Thanks for watching, and I'll see you guys later.